getting back to what Sean mentioned, it's, we know what the limitations are of the current materials that we use, and whether it's concrete or steel, pre-stressed concrete, there's obviously finite service lives associated with these materials. And so one of the greatest advantages of the advanced composite materials is getting the extended service lives. So, having been a bridge engineer for almost 4 decades now, that's what kind of inspired me to come up with the HCB. And here's a shot of just a typical beam before it's shipped out of the factory, and you can see some of the components of it. The strands at the end are just the lifting loops. You can see the galvanized reinforcing steel that functions as the shear connectors. I'll talk more about that. And the rest of the bridge is basically a composite shell. So if we look at basically the components of this structure and the concept of an HCB, it's to develop a structural member using several different building materials and using each material in its most cost-effective application. So what I mean by that is, if you look at the sketch on the right, there's a concrete compression arch, there's a steel tension tie along the bottom, there's a fiber reinforced polymer shell, and then there's the steel shear connectors that allow that beam to act compositely with the concrete deck that's then placed on top of it. So again, we know concrete functions very well in compression. We know steel functions very well in tension. And I always refer to it as a human endoskeleton, where our bones take the compression, our ligaments and tendons take the tension forces, and then our skin provides this elastic containment that keeps everything together and helps transfer the shear forces. Just a brief overview of this particular type of composite. We use what's called a balanced quad knit fabric. That means you've got a fabric that's got multiple layers of unidirectional glass in 4 different directions. So we've got longitudinal, transverse, and then plus minus 45 that gives us our shear capacity, and then usually just a continuous strand mat that gives us some stability. It's infused in a epoxy vinyl ester resin or epoxy or polyester resins, and that what results is really a fiber reinforced polymer material that gives us quasi-isotropic behavior. So we're basically getting the same material properties in every different direction with the balanced fabrics. For the steel, we typically use just galvanized post-tensioning strand, 1860 MPa, same stuff you would put in a pre-stressed beam, but we typically use galvanizing just for the extra corrosion protection. What the benefit of this is, we can cut it to length, any length we want. We put a 90-degree bend at both ends. We lay it in the mold, and the strands are developed in the end of the beam to catch the thrust of the arch. And then it's basically infused in the same laminate as the FRP. So it's really a steel and glass reinforced laminate when we're complete. Here you can see the manufacturing process. They just throw everything in a closed mold, lay in the glass, the steel, the foam. The foam core comprises the interior volume that doesn't contain the arch. Pull vacuum on it, infuse the resin in, takes about a half an hour. You can build a beam a day in each mold. Then you see on the right there, just setting the composite lid on top of it to get the final roadway, or not the roadway surface, but basically a stay-in-place deck one. The concrete we use is nothing special, just a 41 MPa self-consolidating concrete that overdosed with super plasticizers and viscosity modifiers, so it flows out like water. And I'll show you a little bit more about how we fill this later, but with the SEC, you do a J-ring test instead of a slump test, because you basically want it to be able to flow through the beams and fill all the voids. So the benefits of this technology, obviously you get the lighter weight, so you've got reduced foundation costs. It's usually the mass of an HCB is about the same as a steel beam when they're all said and done. It's about 1/3 of what a concrete beam is. Empty, it's about 1/10 what a concrete beam is. Reduced carbon footprint. Again, cement production is the worst contributor to greenhouse gases in the world. Something like 3.2% of all carbon is produced through cement manufacturing. We're optimizing each material. Like I said, we're just using the minimum amount for each component. Greater corrosion resistance gives us a more sustainable structure with less maintenance costs. It's actually simple to design and fabricate and erect, and hopefully when I get done, you'll believe me. And ultimately, we just want to provide the public with safer bridges. And lastly, reducing the burden of infrastructure costs on future generations through the better performance of these materials. So the impetus of this really came back from, like I said, I'm a practicing bridge engineer, and we think about the theory of reinforced concrete. We know that all the concrete that's in tension is going to crack, and basically it's holding the reinforcing steel in place. It's holding the shear reinforcing, the tension reinforcing. But you're going to get flexural cracks and shear flexural cracks that essentially result in like an arch analogy or a truss analogy, where we know there's a compression load path that's going to carry the applied loads over to the supports. So the whole idea behind this was, can we develop a beam where we get rid of all the concrete that actually doesn't serve any purpose? And the simplest embodiment, this is about a 18-meter beam we did on a project up in Maine back in 2009. And so what you see is when you put the shell in place, it's self-supporting on its own. Then we fill the concrete in the rib to get the compression arch. The deck is placed after that, and ironically what happens is when you place the deck, you actually pre-compress the concrete, which is to your benefit because concrete doesn't fail in compression. Concrete fails usually in shear or tension. So by pre-compressing the concrete, we actually maintain the capacity of the concrete at a higher level as we get to the ultimate limit state. I'll show you that later. If we put a quarter point load test on here, what we see is that we get the compression going down the arch, steel tension tie along the bottom, and then the shear is actually carried in tension field action along the webs of the FRP until we get to the ends of the beams where it begins to be carried by the concrete arch and fin. So it's really quite a fascinating load mechanism. This gives you a good example of comparing an experimental load test to a finite element analysis using Abacus with some very high level contact surfaces and nonlinear elements. And you do actually see the tension diagonals for the shear develop from the load point out as opposed from the bearing in, which is sort of counterintuitive what we do with steel, but again, it's basically because of the load sharing mechanism between the FRP webs and the reinforced concrete. When we design them, we actually just design them as a reinforced concrete beam. So the limit states we typically check, we're going to look at the live load deflections, which generally controls, and we solve that problem just by adding more steel. Then we look at the ultimate bending capacity and then also the ultimate shear capacity. And the way we do that is we just we look at strain compatibility and force equilibrium just like we would a reinforced concrete beam. But now we've got a lot more components because we've got the FRP components, we've got the strand in the bottom, we've got a top flange, a bottom flange, the concrete flange. But still, we can look at the linear strain distribution and calculate the forces in each one of these components. You can set the horizontal forces equal to 0, sum for the moments, and you get this nice simple equation that gives you the ultimate neutral axis of the beam. And that's something that'll keep you busy on a Friday night when you've got nothing better to do. But I'm kind of lazy, so I look at it this way. Compression is equal to tension. Compression is equal to 0.85 F sub C prime AB, which is Whitney's equivalent stress block. And our nominal moment capacity is just the horizontal force times the moment arm. And this is what we would do with concrete, right? And if we do this equation, you can basically neglect the FRP shell in the calculation and you'll get within 5% of the answer. And you'll always be on the conservative side. We always do the rigorous calculations so we know what the actual capacity is, and it checks out very well in the laboratory. But again, in terms of just simplicity and being able to quickly design one of these, you can go that route. A lot of the questions we get about HCB are, like how far can we span? We've done anything from 6 meters to 40 meters. Once they're placed, they're 1/10 the weight of a concrete beam with equal capacity. Once we fill it, it's about 1/3 the weight, or similar to a steel beam. There is an inspection manual that we've developed based on the 0 to 9 NBIS rating criteria that we use in the U.S. to do the biennial bridge inspections, and it basically helps identify what's superficial, what's cosmetic, what requires a more rigorous repair procedure, up to when do you need to close the bridge and do something significant. And again, with the composite materials, we've got little or no maintenance, even in extremely aggressive environments. And I'll show you a few examples of that. Other reasons that you want to use HCB, we can place the beams side by side, and we use, in this case, we used a pultruded stay-in-place form that eliminates any deck forming or stripping during the construction process. And again, we get the better corrosion resistance to the deck using these FRP stay-in-place forms. But you can use other kind of SIP forms. We've used steel, we've used precast concrete, we've used also just a regular reinforced concrete deck. They're lighter weight, so again, we can use smaller equipment to pick the beams and put them in place. And again, if you look at the one on the right, this would typically require either a temporary causeway or a 2-crane pick. And you know, in this case, we're setting the pre-filled beams with a single crane. And again, there's lots of other factors that add to the savings and cost. If we can use the smaller equipment, it mitigates the need for right-of-way takes and temporary trestles and environmental permits, et cetera. These are a couple of the standard sections we've developed over the years. On the left, you see a typical highway bridge, either with or without extended wings and a top flange. And then when we get to the longer spans, you see on the right that if we go to north of, say, 22 meters, we would go to what we call our double web box, which is a lot like a U-girder, a precast U-girder you'd see. And we've done a couple of bridges with this section, like 32-meter spans. So I'll show you a couple of samples of a construction sequence and some examples of completed bridges. In this case, this was an 8-span bridge we did in Maine. Typically, I think it was 16 and 18-meter spans. And the reason that Maine selected this was that there was an existing wooden trestle there on the left, and it was load rated to the point where they couldn't actually deliver precast beams on that wooden trestle. So they would have had to build a trestle all the way across the crossing to actually deliver concrete beams. In this case, we could not only could we deliver the beams on the bridge, but we could put 4 on a truck. They still had a barge-mounted crane to do the substructure, so they were able to set the beams, I think about 16 a day, and you know, very rapid erection sequence. Here you can see the shipping. We've done as many as 8 beams on a truck. Again, very simplistic, just nylon slings, nothing special. We usually fill them, just use a hopper. We have fill points about every, I say every 3 to 4 or 5 meters. And usually if we fill from the quarter points, it flows to the ends, and we can always tell when the grout comes through the shear connector holes that it's completed. This is one where we actually made it continuous for live load over 8 spans. So we used a Freycinet hinge where we had reinforcing steel coming out of the piers, and then there's a closure pour between the beams that gets placed with the deck that gives us our continuity for a continuous bridge. Again, standard details, overhang brackets, scuppers, rebar connectors, and there's a nice view from below. So this is the longest bridge we've done in terms of continuity. We've done about 18 bridges through North America, a couple of Class 1 railroad bridges. We've got one bridge in Australia, and you know, always looking for other opportunities. This is I always refer to this as the $1 million photo. The Latvian bridge engineering tradition is that the engineer has to stand underneath the bridge when they load it. Of course, the railroads are insane about safety, so this was not the first load test. We'd actually run the train around the loop for a couple of days before we did the photo op here, and this was back in 2007. So this is the first proof of concept of an HCB bridge. And again, this is designed for a Cooper E100 with all the design criteria in the ARIMA code. We've done bridges on up to a 45-degree skew, and the benefits of HCB on a skewed bridge is that you don't have to have all the diaphragms that you have for a steel bridge, which simplifies your erection and the complexity of it. And also with precast beams, what happens is on a skew, when you drive a truck across it, it wants to load the beam underneath the wheel, and you get reflective cracking in the deck. So HCBs give you enough flexibility to avoid the reflective cracking, but at the same time, they've got enough torsional resistance that you don't need any intermediate diaphragms. And I'll talk more about that photo down the bottom later. We've done this is a pier that we did in Machias, Maine 11 years ago. This has survived a Category 4 hurricane and 11 very, very brutal winters on the ocean front in Maine. This is all composite. It's composite filled pipe piles. It's a 2-span HCB pile cap, and then it's HCB double T superstructure. This shows you another Class 1 railroad bridge. Again, rapid construction. This was, we got an 8-hour track outage to actually take out the old bridge and replace it with a new one. CP did this up in Fernie, British Columbia. We actually had it operational in about 7 hours. There's another one with BNSF out in Colorado. This is actually a 13 meter span. So this is the longest railroad bridge we've done to date. And I like to close up by just showing, like, nothing's really changed. What you see is a burr wooden truss on the bottom left, back from the late 1700s, early 1800s. On the right is a cast iron railroad bridge in Tennessee that was built in 1860. And then you see an HCB above. It's exactly the same structural principles, just better and more efficient materials. And I can't help throwing these comparisons just for the sales pitch, just to give you an idea of how slow it is for us to progress in our market. You see a phone from 1876 versus a phone from 2016. So pretty dramatic difference there. Same thing with aircrafts. In 1903, the Wright brothers' first controlled flight was a pretty rickety little machine that no one would want to fly across the Atlantic. And now we've got the 787 Dreamliner that's just absolutely amazing. So that's what we've done with aviation. Here's what we did with bridges. So this is a CP railroad bridge. The one on the left was the original bridge in 1904. The one on the right is 2014. So 110 years later, you can see how much we've progressed with bridge design and construction compared to aviation and telecommunications. So that's all for HCB.